had a force sensor in a computer and you placed different types of masses on that force sensor, and the computer generated the force that was applied, how much Earth was pulling down on that object. So in my when I actually did it, my force sensor, I had the direction down as up. So most of you have this exact same graph, except yours went down in the negative region, okay, which is the exact same. But you should see the formula being very similar, except yours would have been negative there. So as we can see over here in our data, as the mass increases, you can see that the force of Earth on that object also increases. So if we thought back to, we can kind of hopefully prove who was correct, Kathy or Rich, which we'll talk about on our next slide. Since this is a linear graph, we can say that for every 1 kilogram, the force increases by your slope value, 10.4. And we talked about in our discussion that this 10.4 is very close to a number that we've talked about in the past, which is our acceleration due to gravity, which is 9.81. So we wanted to figure out, if we knew the mass, is there some type of mathematical relationship or something that we could figure out how much Earth always pulled on the object? So we know, again, if we rearrange our formula, instead of y, we say F, and I'm going to change that to 9.81, and our x was mass. Our 5% was less than 5%, so we can neglect that y-intercept. So our formula just turned into this. And then I also asked, I said, the force of Earth is the same thing as weight. So change your force to W. And again, this 9.81 is known as G, the acceleration due to gravity, times M. So if we know the mass of an object, all we have to do is multiply it by 9.81, and then we know the weight, how much Earth is pulling down on the object. So like I just stated on the previous slide, the force of Earth, our one non-contact force, the force of Earth on an object, is the exact same thing as the weight, okay? If we go to the moon, our mass doesn't change. The amount of stuff we're made up of, that doesn't change. But if we stood on a scale on the moon, that scale would actually read less, because the moon pulls down on you less than the Earth. So weight is the exact same amount as the Earth, our one non-contact force. Okay, and again, like I showed on the previous slide, we get that formula. If I ask you what is the weight of a 10 kilogram object, you just do 10 and multiply it by 9.81. To make our life a little easier, instead of always multiplying by 9.81, we can just round that up to 10, and it makes it a whole lot easier doing our calculation. So if we have a 10 kilogram object, if you multiply that by 10, then the weight would be 100 newtons. And so again, just take whatever the mass is, multiply it by 10, and then you know how much Earth is pulling down on that object. So we now should be able to answer who is correct, Kathy or Rich. So again, the scenario was you had a metal ball, a wooden ball, drop from the exact same height. They hit the ground at the exact same time. Kathy thought that the Earth pulled on the both objects the exact same amount because they hit the ground at the exact same time. Rich said, nope, the heavier object, the force of Earth must be greater. And we just saw with our data from our lab, more mass, more force of Earth's pull. And this formula here also proves it. Okay, so we should all be Team Rich, more mass, more force on the object. Kind of a similar example with Kathy and Rich. We have the elephant and the feather predicament. So it says, suppose that an elephant and a feather are dropped off a very tall building from the same height at the same time. We're somehow able to eliminate air resistance. Which object, the elephant or the feather, will hit the ground first? So thinking about this, I'm going to give you some questions to answer true or false to hopefully help figure out which one will hit the ground first. So here it says, test your understanding by making an effort to identify the following statements as either being true or false. So the elephant and the feather each have the same force of gravity. True or false? So think back to our lab with our data. Which one, did all of the masses have the exact same amount of force, or did different masses have different force? Number 2, the elephant has more mass, yet both elephant and the feather experience the same force of gravity. So this one is kind of saying the exact same thing as number 1, but it's also adding in about the elephant having more mass. So I would like to also say, like, maybe part of the statement could be true, but some of it's false. So overall, it's just going to be false if that's that situation. Number 3, the elephant experiences a greater force of gravity, yet both the elephant and the feather have the same mass. Answer true or false. On Earth, all objects, whether it's an elephant or a feather, have the same force of gravity. True or false. The elephant weighs more than the feather, yet they each have the same mass. The elephant clearly has more mass than the feather, yet they each weigh the same. The elephant clearly has more mass than the feather, yet the amount of gravity, the force down, is the same for each. So this kind of goes back very similar to number 2 up here. And the last one, the elephant has the greatest acceleration, yet the amount of gravity is the same for each. So go through, make sure you can answer true or false for all of those really quickly. So hopefully you figured out that all of those statements were false. Both objects were in free fall, and if we could eliminate air resistance on the objects, they would both fall at the exact same rate, just like what we did in that dodgeball lab. It didn't matter if you tossed a ball up or threw it down, the rate at which the velocity changed was the exact same. The rate at which their velocity changes is the exact same. So for every single second, their velocity is going to change by 9.81. So if they were both dropped from rest at 0 seconds, their velocities would be 0. The first second, it's going to be, their velocities are going to be now 9.81. At the second, it's going to be 9.81 times 2. At the third second, it's going to be 9.81 times 3. Every single second, their velocity is going to increase by 9.81. The force of gravity, we've learned from our mass and weight lab, is there is not going to be the same for the elephant and the feather. The elephant has more mass, so Earth is going to pull on it more, just like what when we rearranged our formula, our weight is equal to mass times g, the acceleration due to gravity. So Earth is going to pull on the elephant more than the feather. But again, when we think about our formulas, our F equals ma, okay, their acceleration, their mass is different. Their acceleration must be the same. So the ratio of the force divided by the mass for both the elephant and the feather must equal 9.81. If we obviously all know that their masses are different, and if the force was the same, then different mass, we would not get the same acceleration value, and therefore then they would hit at different times. But we do know, we were told when we did that lab, that they will hit at the exact same time. So like stated here, even though a baby elephant may experience 100,000 times the force of a feather, it has